Good evening, everybody. So we'll have Carlo's talk, probably be around 45 minutes, and then we'll have a Q&A after where we'll stop recording. So you're free to open up with your questions. So Carlo did his undergraduate work in Bologna and got his PhD from the University of Padua. And then, like most physicists after their PhD, he had a series of postdocs, research-like positions. And he was for 10 years a faculty member at the University of Pittsburgh before moving back to Europe, to France, to Aix-Marseille University, where he's head of the quantum gravity group there. He's written over 200 scientific papers, and he has 2 books, one on quantum gravity and one more specifically on loop quantum gravity, of which he's one of the developers. I met him when he visited Syracuse University, where I was before here, and I remember very vividly going to a talk of his where the first hour was a discussion of how basically you can get rid of time. So then the talk started in the second hour, which was wonderful. So we had these classical style talks that go on for a very long time. But this is one of the kinds of things that Carlo thinks about frequently and has written about. As Lars mentioned, besides his technical work, he has written several, something like 5, plus another one, more popular science books. One of them, the one that Christy was talking about earlier, 7 Brief Lessons on Physics, has been translated into 44 languages and sold over 1 million copies, beating out 50 Shades of Grey in Europe. That book came from a series of columns in an Italian newspaper in the cultural section of Il Sole 24 Ore. So it's really nice to see that newspapers still publish deep things like this. One of the reviewers of Carlos's book said the closest thing he could, I think it was a he, pretty sure, could find to this writing was the writing of Lucretius on the nature of things from the 1st century BC. So that's rather intimidating when you have to introduce the Lucretius. In a recent interview Christine Newton did with me, she asked me what I would do to change something about physicists. And I said, well, we're not one uniform species. And I think nowhere is that better illustrated than Carlo in his life, in his work, and his writing. Carlo, it's over to you.
Mark, thank you very much for this extremely generous introduction. Thank you, Lars. Thank you all of you for being here. Actually, boy, I remember that lecture in Syracuse. I was a kid. I remember how worried I was before starting, and I'm still worried every time I give a lecture, even now. But I remember that one. I think it's the first time I gave an important lecture in front of very smart people. But let me add one thing. The first time I actually met a lot of scientists was in Santa Barbara. There was a program, as a university student, I got totally fascinated by the program of quantum gravity. And there was one of the programs of the Santa Barbara Institute, it had a different name at the time. It was on quantum gravity. So I asked her to participate. There was a young Gary Horowitz at the time who was running it. I was a student, so Gary very kindly, because always says, he answered, sorry, I mean, we're already full. I mean, this has been organized long ago and there's no room for you. So I was in Italy. I just jumped on a plane, arrived in Santa Barbara, went to see Gary and say, well, I came from Italy. Are you throwing me out? And he said, okay, you're here now, you can you can participate. And that's how I met the great people of quantum gravity. I met Ted Newman and Lee Smalling and Abhay Ashika the first time in quantum gravity. I remember then. So It's a pleasure and a honor to be in this to be here now, and I've prepared a presentation on black holes, thinking that all you guys who are listening are not necessarily super expert on quantum physics. I'm not going to great detail. So I assume that you know very little about quantum gravity, because that will be the main topic. But I've spotted in the audience also some colleagues and some friends. So I have both part of the audience in mind. So I'm going to present also some ideas in a simple way, but that I hope to be of interest to my colleagues. I'm talking about a part of physics in which, as you know very well, me and my colleagues don't always agree. So there are different ideas, different schools, different directions. In fact, I would hope that in Santa Barbara, people were more open also to other directions. So I'm going to present part of my talk will be on things very well established about black holes, and part will be about what we don't yet know, and on one of the possibilities that we have to ask the open questions. So let me share the screen and start immediately by saying which one are the question I'm going to address. Let's see if this works. Here it is. So the question I'm going to address is this one. Where does the matter that falls into a black hole go? And it's a kind of kid's question, right? It's the simplest question you can ask. We see these things in the sky, the black holes, and we see matter falling in. We almost literally see matter falling in. We see the matter spiraling around the black holes, and we can sort of follow the spiraling down. And sometimes we really see big chunks of matter disappearing, and they go into the black hole. So we are pretty sure that matter goes in, strongly convinced that matter goes in. Very well. We claim that we have a good understanding of what's going on there. So matter goes in, and where does it go? And the answer is that we don't know, really don't know. So it's one of the things that we don't know, because we don't have any theory sufficiently established, sufficiently sort of agreed upon by the community or tested or anything that tell us clearly where the things that fall into the black hole go. So I'm going to tell you what exactly is the problem, where it comes in, why we think there is this problem, and what could be a solution of this problem, and the solution which by far I consider most likely, even if, as I said, not everybody agrees. So let me start from the beginning. Let me check the time. I don't want to go too much. I want to be short also, because I look forward for questions and comments at the end from you. So if you have questions, please don't hesitate. So let me start from a comment which is a little more subtle than what it looks. What are black holes? There are mathematical definitions in mathematical physics books and physics books, but I think, for a reason which I said is subtle, I think the best notion of what a black hole is those things that we see in the sky. We see in the sky objects in a number of ways, which I'll mention in a moment, that we call black holes. And they are some very massive, usually object, very compact, some very big. We have evidence of some which are billions times the mass of the sun, in a relatively very small region. And we even have a sort of picture of them. This is a very famous picture, was on the front page of the New York Times, which was taken just a few years ago with a sort of the so-called event telescope, which is actually an array of radio telescopes. Roughly that funny ring, it's just immediately around the actual black holes. there are a number of ways we have evidence of their existence. What is spectacular, what is really spectacular, is that until not long ago, a few years ago, many were not at all convinced that these things existed. There was a theoretical literature about black holes. When I moved, Mark, remember, I moved from the US to France. So I joined France, and the director of the physics department where I went was a particle physicist, not a relativist. Very good particle physics, an excellent particle physicist, has a splendid results. And I remember the conversation, that was 2000, so 20 years ago. And in the conversation, he told me, Carlo, you don't really believe that black holes exist for real out of the sky, right? The experts were already pretty convinced that they existed, but the evidence was not sufficient for convincing a good particle physicist that was not close to the specific field. Now nobody doubts that these things are there. We have an immense amount of evidence. And the reason the evidence is so convincing is that a lot of things that we see out there are exactly what was predicted by the theory. For instance, they do behave exactly like the theory says. And the theory is general relativity. So for instance, the image I just got is just a sort of out of focus version of the left image in this slide, which is a theoretical calculation of what we would see if we looked at a black hole. And the reason there is this nice circular ring is because light, it's so attracted to the black hole that it spirals, it turns many times around the black hole at one particular orbit, one particular distance from the black hole. So a lot of photons sort of come from that particular orbit. It's called the photon ring. So theoretically, it was predicted that if we look at the black hole, we would see that. And that's exactly what we see. Just a little bit out of focus, but people have no doubts that a little bit of improvement in technology, the right picture, which is the actual picture, will be more on focus and will look more and more like the last one. So much more evidence. This is a sort of real movie. It's not really a movie. It's a sequence of photographs of the stars in the center of our galaxy, which move around. This here they're traced with lines, so you see exactly how they move. And they all move around a point, a really central point. So clearly there is a mass there, and it's easy from the orbits to compute the mass, how big it is, and there are indirect way to see how large it is. And it's sort of 1 million times or 4 million times the mass of the sun in a very small region. I mean, smaller than the orbit of the Earth. So it's, what else could be if not a black hole? We don't have other alternatives to than these things are the object predicted by general relativity. And this measurement is what got the 2020 Nobel Prize to these people here. So last year Nobel Prize. And then the other extraordinary piece of evidence is its detection of the gravitational waves, which has been a fantastic result. This is another Nobel Prize, 2017. It's a fantastic piece of result because not only it proves that there are gravitational waves, which are predicted by general relativity, nobody had seen them, they were desperately searched by the physicists for decades, but also because these gravitational waves were produced by black holes. And we have evidence that most of the gravitational waves that we have detected so far are predicted by this object here. And once again, on the left here, there is the theoretically predicted shape of the hole, which is, it's easy to understand this shape because there are two things rotating around one another. And by rotating, they emit radiation and they lose energy. So because they lose energy, they go faster and they fall sort of to one another. So the wave that emits becomes more rapid. So the frequency increases, but also they emit more energy, so it increases in amplitude. And this gives the characteristics sort of shape of that as a sound, it's a sound that increases in intensity and frequency. Whoop, it's called a chirp. And that is a predicted one, which is copied here down, and the upper one is observed one. And, you know, it's spectacular. It's just exactly what you expect. So these things behave like expected. I have, if you haven't seen that, it's impossible. I don't know if you get the sound. Probably not. Do you get the sound of this?
Yes.
You hear the whoop at the end of the... So this is a transformation in sound of the shape of the actual signal. So this is a sound of black hole, so to say, in some sense. It's this moment in which the frequency goes up, whoop, and the intensity goes up. So there are these things out there. They are exactly what the theory predicted. They're extraordinarily compact. You know, to give you an idea, if you want to make a black hole out of the Earth, you have to squeeze the entire mass of the Earth in 1 centimeters cube, a teeny little thing. They do all these funny things. They bend light dramatically. There are many of them in the sky. The ones we have seen goes from a few solar masses to billions of solar masses. But I would be surprised if there aren't other kinds. You know, we're just discovering black holes of different sizes every few years, if not months. For instance, small black holes. We haven't seen them, but probably we haven't seen them because, for the same reason we hadn't seen them, the big one before. I mean, we have not yet seen them. We don't know. But I would be surprised if we have started seeing them and we've seen all the kind of them. So again, these were behave like we predicted, and predicted by whom? These are some of the, I would say, the four main people in the story. Einstein wrote the equations of gravity in 1915. Very rapidly, Carl Schwarzschild, the year later, find a solution to this equation. This solution is the first of the mathematical equation that we use for describing black holes. Other were found by Ted Newman, for instance, the guy who I saw in Santa Barbara when I came the first time in '86, the Kerr-Newman solution. For a long time, between the 1916 to the 60s, nobody really understood what these mathematical solutions meant. They were very strange. When you go to the small funny things seem to happen, time to stop, distance to become infinite. Everybody was very confused. Einstein had no idea what the solution meant. Einstein thought that at the surface of the black hole, the world ends, really stops there, because he was confused. And in fact, it took decades to sort this out. And some of my colleagues are still confused and make exactly the same confusion I said, don't realize that. But this was completely clarified in the 60s by a number of people. David Finkelstein is one who played an important role. There are others. At the beginning, until that time, it was suspected that these solutions were very peculiar because it was a very symmetric solution of the equations. But the work of Roger Penrose, who got the Nobel Prize essentially for that, convinced everybody that these are not generic, these are not special solutions, these are pretty generic. Once you take sufficient mass, squeeze enough, you create these kind of things. But, so let me put my hands in the plate here and try to tell you what is actually happening in a black hole according to the theory that described them so well. And I'm going to use space-time pictures. My colleagues know these pictures very well. You probably have seen them. But let me just introduce them. It's very simple. On the horizontal line, I put a different position in space. Suppose that the black hole here is on the left. So this woman here is at some distance. This man is a more distance. When I'm more to the right is a more distance. Up here, I put the same story later. So at a later time. So time goes up and space goes in a direction. So the first thing you can imagine is that on this line here is the center of a black hole. This is the boundary of the black hole. The black hole is inside, is on the left, and the outside is on the right. So this is the border of the black hole. And if you're outside, you see the black hole at some distance from you. But then funny things happen. And one of the things that happen, which is that probably know very well that one of the great predictions of general relativity is that time doesn't go at the same speed, depending on where you are. If you are on the mountains, there's more time passing that by the sea. So you guys near Santa Barbara, you have more time than people living up in Boulder, Colorado. You have less time than people living in Boulder, Colorado. So the more you go near a mass, more time slow. And if you do the calculation, when you go very close to the boundary of the black hole, time goes extremely slowly. And in fact, the clock stops there. It's very confusing and very unclear. And if you go inside, something seems to be funny with space and time. It took, as I said, it took a while to understand what it is. What is funny is that in this picture here, if this person moved to the future, it can stay at a certain distance from the black hole. But if a person moved to the future crossing the boundary of the black hole, his or her future necessarily points to the center of the black hole. So the point is that the one I gave you is a bad picture. This is a best picture. The boundary of the black hole, it's actually something that separates the past from the future. Once you go in, you cannot come back for the same reason in which you cannot go back to yesterday. Okay, the inside is the future of the outside. All points no point in the inside has a future point which is outside. Okay, so this is really the boundary of the black hole. If you're here, you can only go up. And where do you go? Where is your future? Well, your future is what you call the center of the black hole. So you just you cannot avoid moving to the center because you cannot avoid moving to the future. And this line here, which is the surface of a black hole, I drew it in this way to say that the future is up and the past is down, but it's not a line that moves in space with respect to somebody outside. It's a line which represents the boundary of the black hole, the horizon. The black hole itself is formed by a star that collapses. All the black holes that we see in the sky, we expect that they were formed by a star sort of ending burning, and the heat keeps it up, and then when the it's over, its weight makes it compress. So at some point it becomes very, very compressed. It creates a black hole and is inside the black holes, and it goes to the center, and everything else goes to the center after that. Now, what's the shape inside? What is the shape of space inside? Remember that a black hole is it's round, right? So a point here of its boundary is actually a little sphere, and all these points along this line is actually the surface of black hole at different times. The horizon of the black hole, the sphere that surrounds the black hole at different times. So what's inside? Well, a little bit of mathematics shows that one possible way of representing the inside is this one. So take the black hole at some moment. Okay, so it's a sphere. Here I draw it like a circle because to make it simple. Inside is like a long tube, a very, very long tube, a very long, narrow tube. And at the beginning, this tube is larger and shorter. And as time passes, the tube becomes longer and more narrow. When you go very far in the future, it becomes extremely narrow, and in the center, it just collapses to a point, okay? The center being in the future, remember. So this is a strange and curious geometry of a black hole. If you fall in, you fall in one point, you have no options that going, you just do nothing, and time passes, and you find yourself in the center. The actual time that passes for you is very short. I'll come back to this. So you go to the center in a very short time. But if you're outside, you can sort of throw one stone in the black holes, throw one stone in the black hole later and later and later. You can keep doing that for a very, very long time. Okay? So all this very curious space-time geometry, it's what the theory predicts. It matches what we see today, and we think that it's completely reliable. Now, to be sure, remembering my director in France who didn't believe black holes, and remembering the confusion of Einstein and the confusion until the 60s, at first nobody understood all that, right? Einstein was completely confused about that. In the 40s, 50s, we have a count of conferences where people debate these things, like they debated whether gravitational waves are real or not, and people saying silly, great physicists saying silly things about that. So it has not been easy to unravel all that. But today, all what I said so far is uncontroversial. It's, everybody who studies general relativity and teaches a course on general relativity says this is what we understand of black holes. This is what the theory of Einstein predicts, and this matches with everything we see. Now, let me say something about white holes also, because they're going to play a role in a moment. Let me say immediately white holes are not something that we have seen, but they're also a solution of Einstein equations, like black holes. And also, it took some time to understand what they are. And also, for a long time, people didn't think that they represented something real. So perhaps they don't represent something real, but perhaps they do, like black hole did for a long time. So what is a white hole? It's just what you would get if you make a movie of a black hole and show the movie backward in time, in reverse. So a white hole is it's a solution of Einstein equation, is some possibility for nature predicted by Einstein equations, where you have a region with a boundary, so you still have the sphere. It's also a sphere, like a black hole. It's a ball there, okay? But instead of being something where you can only enter, it's something from which you can only exit. And drawing it in the way I drew a black hole, so making the proper future going up, this is a picture of a white hole. So the center is here, and from the center, things come out. Like in the black hole, everything dies in the center. Here, things are born out of the center. And once you are inside, you have sort of no options that at some point coming out, or you have to run a lot to try to come out as late as possible. And there's no way to go in, because when you're outside, the white hole is always in your past. A good question is, do these things exist in nature? Once again, everything I've said so far, it's uncontroversial, including the fact that this is a good question. I mean, do these things exist in nature? These are also predicted by Einstein theory. So far, I've just, how much time I've used? Too much. So I should go a little bit faster. So far, everything I've said is, it's just accounted for general relativity, classical general relativity. But of course, we know there is quantum mechanics. And quantum mechanics comes in and changes the story a little bit. And quantum mechanics change the story in two different ways, two very conceptually separate ways. One is that there is quantum matter, and this is an effect I'll say in a moment. And second, that there are quantum effects of space-time. There is quantum gravity, which is my job. It's what I've done all my life, quantum gravity. The quantum matter part, it's sort of well understood. It's not tested, but there is a lot of agreement that to a large extent, what are the quantum effects and what they do, at least to a good part. Because the first one to understand that was Stephen Hawking in the early 70s, but then his calculations have been repeated in all sorts of ways, and they seem pretty consistent that that's what it is. The quantum gravity part, it's still at the boundary of what we know. It's more controversial and is the most interesting part. So let me say something about the effect of the quantum matter, and then talk about quantum gravity. Well, the effect of the quantum matter is it's well known. It's in fact the black holes emit radiation. This is the famous Hawking radiation. They became as if they were hot. So the quantum fields, the quantum matter outside the black holes, get excited somehow and radiates away energy. And this energy is taken away from the black hole itself. And as a consequence, the black hole shrinks and becomes smaller and smaller and smaller. And this is the Hawking prediction. And we sort of all agree with theoretical physicists that that's likely what's going to happen, a black hole alone, isolated out there with nothing falling in the empty space. It's going to be slowly shrinking and becoming smaller and smaller and smaller. Now, it's a little bit funny that it's hot. What is hot there? There are various ways of viewing it, depending on which religion are you in physics, which school are you in physics, the one who dominates in Santa Barbara, or the one who dominates in Europe, or that dominates in perimeter, or dominates in Penn State, or wherever. You have a little bit different ways. One possibility is in quantum gravity, which is what I consider the best theory of quantum gravity. It's to remember that space-time is granular at small distance. Space-time is made by little quanta of space, which are connected to one another. So these little balls are discrete pieces of space-time. Like the electromagnetic field is made by photons, it's granular. The gravitational field is made by quanta, but the gravitational field is space, so space is made by quanta. So imagine that space is something like that at very small scale. It's just a lot of little discrete things being created and destroyed. If so, the surface of the black hole, which is just a region of space, it has little quanta of space. If you count the quanta of space, say what they are, they behave like the gas in a room, having many molecules, and the motion of these molecules giving temperature. So the motion of this quantum space on the surface of the black hole can be related to the temperature of the black hole. So one can imagine, and this is very pictorially and not very precise, that these things move somehow, and that's where the radiation comes from. Whatever is the reason, what actually happened is that if you put there a black hole for a long time, the size of the throat becomes smaller and smaller and smaller in time. And that's what I said, it's a more or less agreed story, this shrinking of the black hole. Now, what about quantum gravity? Well, the question is that quantum gravity is irrelevant most of the time, most of the space-time. We have good reason to believe that quantum gravity don't play a role. Perhaps it might play a role sometimes just outside the black hole before. Some speculation. Steve Giddens in the audience, I saw his name. He has very intriguing ideas and beautiful formalism on which to study the possibility that there are some quantum gravity effects that come early, just outside the black hole. I've also explored some possible ideas of that sense, but this is very speculative. What we know for sure is that quantum gravity comes in heavily when the curvature is large. And the curvature is large means near the center of the black hole. Because you see, this little cylinder here is curved, and the more you go in, the more it's curved. I mean, I'm talking a little bit precisely here, but it's a fact that the more you go to the center, the more space-time is curved. So you definitely go to a region where quantum mechanics cannot be disregarded. Not only that, but if you're outside the black hole, you keep outside the black hole, the hole becomes smaller, 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 and at some point the curvature grows and becomes such, we say Planckian, because such that quantum gravity comes in. So at some point in the future, quantum gravity comes in, okay? What about a white hole? Well, imagine that there was a white hole. In the past, at some point, quantum gravity was relevant here. Well, suppose you don't know anything about quantum gravity, but you know something about quantum mechanics. Quantum mechanics tell you that things happen with a certain probability, even when they always happen, unless something is really forbidding it. Once you go in a quantum regime, you have a phenomenon which is called tunneling, which allows things to go through a wall, radiation to escape from an atom. Things happen with probability in quantum mechanics, and this probability becomes big when you're in a quantum regime. So here things can happen, and here things can happen. Well, there is an obvious suggestion here that what happens once you enter into the black hole may be what happens before you come out into white hole. So it may be that this is a story, that once you fall in the black hole, you go to the quantum region, you violate classical generativity because you're entering in a quantum region, but you rapidly find yourself, like in tunneling, once again in a region perfectly described by a classical generativity, and that's the white hole. And this is a possibility which quite spectacularly, nobody expected that, this is a recent result, it's compatible with Einstein theory outside in the white hole and the black hole. Namely, it's possible to, Einstein theory does predict this possibility to have a black hole evolve into a white hole, provided that a little bit of quantum freedom is allowed in a teeny region that join the two, okay? Which of course has to come out from the black hole, because otherwise when you're a black hole, you would never quantum tunnel into a white hole. So you have quantum gravity to allow yourself, to give you the freedom for this transition, both near the singularity and outside, in all this blue region here. And this is what loop quantum gravity predicts. In fact, not only predicts, but it gives you tools for computing this, the probability of this transition. So here is a scenario which might answer the question of the title. Where does the matter falling to black hole go? Okay, does it disappear in the singularity? Does it go to a different universe? Is it destroyed and forgotten forever? No, nothing so dramatic, something much more simple. It falls in the black hole, it goes to the quantum region, it crosses it, like, tunneling, you can cross things. It finds itself in a white hole, it comes out. That's a concrete scenario. Is this a real thing that happened to a black hole in a far distance? I think it's a very realistic possibility worth studying. I'm spending time doing the mathematical calculation of the transition amplitude here. Some colleagues of mine don't consider that realistic because they have what I think are prejudices. And we're debating and discussing about that. Steve Giddins, the audience, we're exchanging mails about that in this very period. All right, so that's what loop quantum gravity predicts about the evolution of black hole. Now, what would you see? What would I see if I'm outside? Well, not much. The star collapses. This is the black hole, the black sphere, the same. I can take pictures like the one taken by telescopes. At some point, there is a quantum transition, is a white hole. I mean, nothing changes from the outside much. But here, I can have things falling in. Here, there are things that may come out. And in fact, what comes out is exactly what fell in. Inside, you imagine this tube, which becomes longer, transition, and then becomes shorter, right? And the star is in the bottom of this tube, so at the end, the star can come out, the matter of the star. Maybe compressed, maybe the energy, things have happened, of course. Energy has been taken out by the Hawking radiation, so the total energy has decreased. There is a complicated story to be studied, energy balance, information balance, the actual fields in this various time slides. And this is the work which is being done. Now, last, and then I close. Suppose this is true. Can we see something? And let me tell you what I think is the most exciting part of this story, and just to conclude, and what leads us to possible observations, and which I insist have not done yet. But, you know, that's what we want. We want to develop theory and then come with observations. But there's a magic part of the story. Remember that in general relativity, you know, a clock in the mountain and a clock by the sea go at different speed. If you go near a black hole, a clock goes slower. So you can take this geometry, this story, and imagine that the woman here jumps inside, is sufficiently solid to resist enormous pressure through this region, has a clock and comes out, and the man stays outside. Okay, and then they can meet again, of course. So they are, suppose, sister and brothers, roughly as the same age. But because of general relativity, as you know, you've seen Interstellar, when they meet, one is older and one is younger. So imagine this is a black hole of the size of black holes within the sky, or one of the smaller black holes that maybe was produced in the early universe. And I do the calculation of the difference of time. So you expect the girl inside to be young and the man outside to be old if they were the same age before. But if you do the calculation, inside it's of order of a millisecond, outside is order of a billion of years, billions of years, okay, for a mass hole, for a big macroscopic black hole. Which means that essentially, you know, a black hole, from this perspective, is a little tunnel into the future. It's a shortcut to the future. You jump in, and zoom, immediately after you jump out, and outside, billions of years has passed them. This is what a black hole is. And this forces also a very long time for the black hole to shrink, and extremely even longer time for the white hole to remain before coming out. And this has a remarkable, so a black hole is a shortcut to the future. This has a remarkable consequences because for two reasons. Let me skip this. I want to arrive at the end. First of all, this remnant, this long, very long-living white holes here that might be very small, because remember, the black hole has become small. Now it's very small, and now it remains small for a very long time. So the theory predicts that there are little things out there. The smallest they can be is a microgram, which is that's what quantum gravity predicts. Little grain of dust of a microgram, very, very long living. There are these long tubes inside that slowly they're coming out. Now, so the theory predicts that there is a sort of powder which only interacts gravitationally, and it's all over. So it's a sort of dark matter, where it happens to be that in the universe is full of dark matter. So of course, we don't know what dark matter is, and there are many hypotheses of what dark matter is. This is one hypothesis of what dark matter could is. It's a bit different than the other hypothesis, because most of the other hypotheses depend on some physics some new physics, some hypotheses, you know, some supersymmetric particles, nobody has seen supersymmetry, some modification of Einstein equation, nobody has seen modification of Einstein equations. This, which is just a speculation, certainly not something sure, but it could be a phenomenon predicted by just general relativity quantum mechanics, the physics we know. No additional physics for accounting for dark matter, which is one of the great mysteries around. But we could even be more lucky here, because if the black holes formed in the early universe, and there is increasing evidence that there are primordial black holes, because in the very early universe there's a lot of energy density, a lot of fluctuations, so it might well be that the black hole formed. And the photons, the very high energy hot photons there, would jump into the black hole and would come out now, much later. So this could give radiation coming from the sky out of this little remnants that we could observe. And there's a phenomenon, I don't have time to go through the math, it's not complicated, but it's just a few steps, that these high energy radiation might have a very peculiar, because of the mechanisms that produce them, curve of the wavelength as a function of distance from which they are produced. So they might be a very clear signature, sort of smoking gun, as the people in astronomy say, that would characterize them with respect to all other phenomena. Have we seen them? Not yet. We see a lot of gamma rays. We don't know where they come from, but this hasn't been, this curve hasn't been detected yet. Are we sure that this dark matter is remnant? No, of course. There are many other possibilities, but it might be that these marvelous things, which are black holes, are still far from being elucidated from the recent observations. And the question we have them open might still have answer that can be tested with observation, like it has happened in the last years. So that's my last slide. In short, the upper part is it's black holes. They were theoretical when I was a student. We just ask just this: the book where I studied generativity by Steven Weinberg, one of the great physicists of generation that did great physics in the 60s, 70s. It's a fantastic book, published in the early 70s. There were already some hints about black holes. The book says, most likely there are no black holes in the sky. Okay, it's a clear explanation of black holes, but it considered unlikely because of the extraordinary density needed for them. Just wrong. So the theory predicts these things, predict absolutely strange space-time phenomena. Everything has been verified so far. If you fold quantum gravity in, you have the possibility that black hole evolves into white hole. In particular, loop quantum gravity predicts that, allows us to compute the probability for this transition. It may give observable phenomena. They are not yet verified. This is physics. Stay tuned. We hope in the next year to know more. Thank you.
Thank you, Carlo.